Okay, so we are looking at 129 office hours. We've got our list of questions we're going to address. Let's go ahead and let's start with 5.2, that problem that keeps coming back to haunt us. Who can tell me what 5.2 number 3 is asking? Can someone, you got it handy?
Yeah, it says a buffer is prepared by mixing 400 milliliters of 0.31 molar HCl and 500 milliliters of 0.49 molar sodium acetate. And then it asks what's the pH, and then how many grams of KOH must be added to change the buffer by 0.15 units.
Okay, and I know it's 0.15 because we're adding hydroxide. Okay, so we are making a buffer and then we are modifying the buffer. This is a weak base strong acid buffer, so not that different from things we've done before, but just slightly different. So let's go ahead, let's figure out the buffer. Let's do part A, which is figuring out the pH of this thing. So I know, I'm gonna do, wow, it feels like it's been so long since I've done this, but of course I'm gonna start with thinking. Right, and I'm gonna grab my calculator. Hand me that calculator. I have like I have so many calculators in this room, and somehow they're never next to me. Okay, so I'm going to go ahead, I'm going to do the thing now. There's nothing in the problem that asks me to do this, but I'm going to do 0.41 times 500. 0.41 times 500 divided by 0.31. So to get to the equivalence point is 661 milliliters. Divide that by 2. 330 milliliters to get to, oh wait, let me flip this over real quick.
Dr. Erker, I think it's 0.49.
Oh, is it 0.49? Okay. That's going to change numbers a little bit. We all should have different randomized numbers anyway. Let me just do this again. 500 times 0.49 divided by 0.31. So I get my total moles, which is 500 times 0.49 divided by the 0.31. That gets me 790 to my equivalence point. Let me draw that a little bit better. Steep drop. Divide that by 2, and I get 395 to my midpoint. Since this is an acetic acid acetate combo, I know that is going to be 4.74. So I'm expecting my pH to be, wow, okay, 400 milliliters is just a little bit past my midpoint. So I'm going to expect a pH that's just below 4.74. I'm going to say my pH is going to be 4.7. Right? That's my thinking phase. That's me kind of considering, like, what do I think is going to happen. I can do this in 2 steps or 1 giant step. I'm going to start doing it in 2 steps since I feel like I haven't done a buffer problem in like 3 weeks. So let's take some time to do that. We're going to have AC minus plus H3O plus goes to HAC. And this is going to be my millimoles, 0.49 times 500. And this is going to be 0.31 times 400. Get my start of my stoichiometry. 0.49 times 500. That's 245 millimoles. And then 0.31 times 400, 124 millimoles. Don't really care about the H2O being made, but it's there too. I'm going to have minus 124, minus 124, plus 124, plus 225. That gets me 121, 0, 124. Are we okay with that stoichiometry? Then I can just say pH is equal to pKa. I'm in the buffer range. I've got weak acid and conjugate base both present. So I can say pH is equal to pKa plus log of A minus concentration divided by HA concentration. And then I plug in my values. This is going to be 4.74 plus log of 121 over 124. Again, I've canceled out, I should divide by volume total for both of these to get it to concentrations, but dividing by volume total on both sides just cancels out. So I just get 121 over 124. That'll get me on my pH, which I'm expecting. Okay, maybe it's only 4.72, but let's go ahead and calculate. 121 divided by 124 log plus 4.74. Yeah, we get 4.73. So my estimation was a little bit off, but we get this is equal to 4.73. That's my answer. Ta-da! For part A.
So the real difference between, you know, weak acid, strong base, and strong base, or strong acid, weak base is like when you put it into Henderson-Hasselbalch, it's kind of like flipped from what you normally put in. Like I'm saying, like the A minus is always on the top, but
A minus is always on top.
But in the answer, like A minus, or in
the
story,
reactants versus the products, the stoichiometry is flipped.
Is flipped, right?
That's the part I would say. It's
yeah,
not
that's
Henderson-Hasselbalch's change, it's the stoichiometry is flipped.
Okay. Thank you.
Yeah, absolutely. That's pretty much the only thing that has changed is we're doing a different chemical reaction. Remember, most of the problems, up until we started doing this orbital stuff, most of our problems break down into what's in the beaker, what reaction is happening, what equilibrium is established. And it's kind of like those things have been what we've been doing all quarter. And we toss in a little bit extra, like, well, how could I control that how could I control that equilibrium? How can I change that equilibrium? Which is what part B is about. Any other questions before we try part B? I assume most of the questions are about part B. So for part B, I'm going to keep almost none of this. I'm just going to keep, I have to do a different chemical reaction. So here's what I'm going to keep. I'm going to keep this excess stuff. So after the reaction is done, I have this 121 and this 124. 0, don't care about that. Right? That's where we were at the end of the excess step, at the end of the first reaction. And now we want to do a second reaction where I'm throwing some potassium hydroxide on there. And there's two different conceptual ways to think about how that's going to do it, what change that's going to make. First obvious thing, you're adding base. That's going to send the pH up by doing by strong base reacting with weak acid, so my HAC should get smaller. Equivalently, and I haven't really done it this way, you can imagine it's just like adding less acid. Right? That would be kind of equivalent. Like if I just added less acid, that would be like adding base. What was our answer for pH? I should have kept that as well.
4.73.
Right, so we got our pH of 4.73. Now we're going to do a new chemical reaction where I'm going to dump hydroxide in. Is hydroxide going to react with AC minus? It's going to react with HAC. So I'm going to have new stoichiometry. I'm going to have HAC plus OH minus goes to AC minus plus H2O. Where I've got 124 here for my start. I've got some unknown number of moles. I'm asked how many moles, and I've got some 121 here. My reaction step would be minus moles, plus moles, and I'd get 124 minus N, get 0, and I'd get 121 plus N. And this makes sense because when I add base, it uses up some of my weak acid and converts it into conjugate base. And then I'm still in as long as I don't add too much base, I'm still in the buffer range. I'm still going to end up with pH equals pKa plus log of A minus over HA. And I can plug in my HA and my A minus, because we're using the X is small approximation, which we're allowed to do in the buffer range, I'm going to get pH is equal to 4.74 plus log of 121 plus n divided by 124 minus n. I have to solve for n. Now, right now, I've got two things to solve for. I don't have my pH, I don't have my n. But I know I want my pH to go up by 1.5, so I can actually figure that out. What's 0.15 bigger than 4.73? Calculators. What is it? 4.8. 4.88. There we go. So I can calculate this 4.88 for my answer to part A plus the information given in part B. Now I just got to do the algebra. Solve for my moles of N. Does it ask for how many moles of potassium hydroxide or grams?
Grams.
So after we get that moles, we'll have to multiply by molecular weight to get grams, an extra step in there. So keep in mind we're solving for moles, not grams, but we can solve for our N. Just doing the algebra. I lost my calculator again. Is it above my head? There it is. Okay. So let's go ahead and do this. And remember, actually this one doesn't have a nice set of steps. 4.88 minus 4.74. Oh yeah, because we're off by the acid we threw in. I was like, why isn't this 4.73? Remember, this is my Ka, not my made pH. And we added a little bit extra acid because we were a little bit past the midpoint. So I get 0.14 to the power of 10. I can't solve for n as fast as I thought I could. I have to do this in steps. And I get 1.38 is equal to 121 plus n divided by 124 minus n. And then I have to do some rearranging. Times 124 minus 121 divided by 2.38. Is that on the camera? Yeah, barely. Okay. We don't need as much empty space above. We can do it like there. Okay. If I did my calculation correct, I don't know if anyone's double checking me. I wouldn't trust just one person doing a calculation, even if it's me. I got 21.08 millimoles. Remember, since I left that 121 and that 124, those are both in millimoles. So my answer comes out in millimoles. Questions? Yeah. Familiar? A little rusty after the break? How are we going to do this in semesters? You all, most of you will be graduated before then, right?
When are they switching?
26.
Yeah, so fall 26 will be on semesters. It's just like, imagine if this was just on top of half of 125. And we're like 15 weeks in right now. Exciting! I prefer the quarter system, but I'll adapt. Okay, so that is how we do 5.2 number 3. There's a lot. Now, these buffer problems, to keep in mind, that is a lot. There's a lot, like, if you want to see people's jaws drop, do a buffer calculation for someone who's in Chem127, and their minds are like blown. And it's just incredible to me that it's like 20 weeks later, and you're like, oh yeah, buffer calculations. Right? We've done so much. This isn't the culmination of these 10 weeks. This is like the culmination of like the entire Gen Chem series, being able to identify reactions, stoichiometry, equilibrium, modifying the equilibrium by adding stuff on top of it. Like this is big. This is like a lot of stuff to put together. So if you're having a hard time with it, don't be angry with yourself. Like, realize that you're doing like a combination of not just what we did this quarter, but like the entire year of chemistry. On to 6.1. No rest for the wicked. On to 6.1. Okay, I'm going to erase all of this. No screaming no. Okay. So 6.1 number 9. Who wants to tell me what 6.1 number 9 asks?
It was like one of the problems on the quiz
Okay.
about
It was like, I don't know how to explain it. It's like,
Let
it
me
gives
see.
like these structures,
Oh, okay.
and then you have to rank the concentration of each species, find the equilibrium concentration of each species plus the pH. And it gives you the pKa values.
Find the equilibrium concentration. So this is a diprotic acid with a certain pKa. And we want to rank the concentration. Will it be acidic or basic? Find the equilibrium concentration of each thing. Yeah, so this is like a equilibrium series. Okay. Yeah, so this would be an equilibrium series. So I'm going to go ahead and simplify this down to just H2A. Has some equilibrium with water to form HA minus and H3O plus. And let's just focus on this first equilibrium. Forget all the extra steps for a moment. What's our concentration of the acid at the beginning?
I think it was 0.1.
This is our initial. Notice this has no stoichiometry to it. It's just asking us to understand equilibrium in multiple different steps. What's our Ka value for this reaction?
wait, so would this be pKa 2? Or pKa
This is the first proton being lost, so it'll be pKa1.
4.21.
Which I can turn it into Ka1 by doing 10 to the negative 4.21. 4.21 negative to the power of 10. 6.17 times 10 to the minus 5. Minus x plus x plus x. Approximately 0.1 x x. Ka equals x squared over 0.1. X is equal to. Yeah? Times 0.1 square root 2.48 times 10 to the minus 3. Then I do my second proton. Now my second proton is going to have something a little bit quirky happen, right? I'm not adding acids and bases to force this thing to happen. I'm not adding extra conjugate acid to force this thing to happen. I'm just saying when I put this into water, how much does this second proton interact with water? So I'm switching colors to make it stand out a little bit more. HA minus goes to A minus plus H3O plus. How much HA minus do I have in solution? I didn't add any originally. So where's my HA minus come from?
The part that's broken off.
The disassociation. So my HA minus starting concentration, my initial concentration of HA minus in that case, is going to be like 2.48 times 10 to the minus 3. What's the pKa for this one?
5.63.
Oh, that's not much different. 5.63 negative to the power of 10. Oops. 5.63 negative 10. That gets us a Ka2 equal to 2.34 times 10 to the minus 6. Those are pretty close to each other. I know why they did that. In terms of a titration, this would be pretty gnarly. I think you'd end up with a giant smear. Your first buffer range and your second buffer range overlap. So if we wanted to do a titration with this, it'd probably come out a little gnarly. But that's not what we're doing right now. I've got zeros there. I'm doing my change. Minus x plus x plus x. My my equilibrium, I'm going to have approximately 2.48 times 10 to the minus 3 x into x. I'm worried. Can you tell why I'm worried?
X is small, might fail.
I think x is small is going to fail. Let's check what happens. I'm going to have Ka2 is equal to x squared divided by 2.3. Oh, wait, wrong number. 2.48. Wrong 2.4 number. 2.48 times 10 to the minus 3. I'm going to solve for x and see what value I get. My x is small might fail. So I'm going to have 2.34 times 10 to the minus 6 times 2.48 times 10 to the minus 3. Square root. We're mostly okay. I was a little bit overly cautious. We get 7.62 times 10 to the minus 5. That is, let me see, what percent difference is that? Divided by 2.48 times 10 to the minus 3. It's like a 3% error. I think we're okay. It's less than 5. We're okay. So I was right to be worried, but turns out it's okay. We're looking at like a 3% difference. All I did to do that was I took my x value divided by my initial concentration to see what the percent difference was. It's not technically a percent error, but it's a good way to estimate how close we are to x is small failing. So, what does the question ask?
The first one's talking about ranking the concentration of each species.
Okay, well let's go ahead and look at what we got for concentrations of each species. My H2A is approximately 0.1 still. I use my x is small approximation. My HA is approximately 2.48 times 10 to the minus 3. Because I've got, again, I'm using x is small approximation. My A minus is 7.62 times 10 to the minus 5. And this kind of goes with some of the intuition that we've already developed over the quarter, which is this idea that the first proton disassociates the least. Disassociates the most, and then each one after is less than, like, the first proton is strongest. Question?
On mine, I used the second Ka for the equilibrium concentration of A2 minus, and it worked. It wasn't that 7.6.
Yeah, mine's saying the 7.6 is wrong.
It's just like the second Ka of 2.34.
Wait, may I see the problem again? Did I read the problem wrong? Okay. Find the equilibrium concentration of HA minus. So which problem is it doing this for?
On E.
E. Find the equilibrium concentration of K2A. Why would it just be 2.34 times 10 to the minus 6? 5.6 times 10 to the minus 3.
Doesn't we already have H3O plus in concentration?
Oh, I messed up. That's why. Yeah, you're totally right. When this second disassociation happens, is H3O plus equal to 0? No! Right? I was getting too far ahead of myself. I was thinking about the next part. This isn't 0. This is where my mistake is. Right? I have some H3O plus present. So this disassociation is not going to happen as much as I thought. I need to change that 0 to be not 0 and rearrange this entire thing. So let's go ahead and fix it. I'm going to do all my fixes in orange. This is also going to be 2.48 times 10 to the minus 3. And you can see mathematically why we end up with Ka, because this is no longer Ka squared. This is x times 2.48 times 10 to the minus 3. Guess what x is equal to in that case?
Same as.
It's equal to Ka, to Ka2. 2.34 times 10 to the minus 6. This value becomes I'm going to put a circle around this because I fixed it, a circle around this because I fixed it. 2.34. And my x is small approximation is definitely good. Thanks for noticing that. Totally forgot that of course we have H3O plus. We already did the first disassociation.
The last part, finding the pH of the solution.
Yeah. So here, I have to take my x value, well, it's really just the green value, right? Technically, it should be the green value plus the blue value, but I'm using the x is small approximation. Sorry, this should be, that should be 2.48 times 10 to the minus 3, right? Since I'm using that x is small approximation, I could say it's just that 2.48 times 10 to the minus 3. You could try adding in that 2.34 times 10 to the minus 6 and say, well, what if we did include that? It shouldn't significantly change your pH.
Wait, so you add that as that would be the concentration of H3O plus?
We could. I don't think we need to do that because, you know, if you're looking at this calculation in blue,
right.
We're using the x is small approximation. And so my H3O plus concentration total should be completely decided by the green calculation, that first proton disassociating. And what I was saying was, if you added in that second equilibrium's value of H3O plus, I don't think it's going to make a difference.
Right.
In this case.
Yeah.
Other situations that might have an impact.
That's what I was about to ask. Like, so on the quiz, my pKa's were really far apart.
Mm-hmm.
So I'm just curious, like, what, like, how does that impact the problem? And what's
the further apart the pKa's are, the better the approximation that everything is done in the first step.
Okay.
Right.
So does it change?
So I did
Like
something completely different from what you
which
did.
species is most
I
present?
found
Like is
the
H
plus
what is it?
concentration.
H2A always going to
You
be
can follow my
most
graph.
present?
Yeah.
H2A is almost always going to be like the first acid. So whether it's H3A or H2A, H4A, whatever our first proton dissociating is, that's going to be our most present. The thing that might be weird about that case, when your Ka's are really different, is if your H3O plus concentration ends up bigger or smaller than one of the other components. Right, so here, with these approximations, my HA concentration and my H3O plus concentration are the same value.
Right.
So like, hopefully there's an option that's like, this one is bigger, then these two are equal to each other, and this one is smallest. Something like that is an option. Is that an option?
Not an option, but I agree.
Well, if we wanted to, so let's say, okay, how would I pick the order for HA minus versus H3O plus? Because right now I have them as the same value, but which one is actually going to be bigger on a conceptual level, not mathematical?
Yeah, H3O plus isn't in the problem. Like, they're not asking.
Oh, okay. Well, then don't even worry about that.
Present, but
Okay, cool.
Yeah, sorry, I was.
Yeah. I think that's a really interesting thing to ask, so I should probably add that in.
And then I'm assuming. I mean, it says will the solution be acidic, basic, or neutral? I'm assuming acidic, just 'cause
Acidic.
we're adding acid to
Yep.
water.
We're adding acid to water, we end up acidic. Yep. So that was 6.1, number 9 for Chem129. 6.2. Oh, ready for it to go away? Okay. Uh, 6.1, number 9. 6.2, number 2. Who's got a read on that for me?
What would be the overall equilibrium constant for the reaction of hydrochloric acid with copper to carbonate?
Hydrochloric?
Did I read that wrong?
It does say hydrochloric.
Yeah.
Oh, wait, let me see. What would be the overall equilibrium constant the reaction. Oh, yeah. Okay, this one's a little bit more complicated than I thought. So this is combining stuff we did from the beginning of the quarter with the stuff we're doing at the end of the quarter. We've got what looks like 3 equilibrium where we only have to worry about 2. So I've got my HCl disassociating into H3O plus Cl minus, and that's definitely happening. That's completely happening. That's the equilibrium we don't need to worry about. Then I've got, which was it, copper?
Yeah.
Copper 2 carbonate?
Yes.
Copper carbonate is going to go through some disassociation into copper 2 plus CO3 2 minus, and that's going to have some KSP associated with it. But then this H3O plus and this CO3 2 minus make an acid-base equilibrium phenomena, and so I can have H3O plus CO3 2 minus goes to H2CO3. Oh, sorry, HCO3 minus plus H2O. And this one, what equilibrium does this look like?
It's a reverse of a Ka.
Yeah, this is going to be a 1 over Ka. Right, because HCO3 plus, or HCO3 plus H2O donates that proton. So then I can just put these two together, and I can do like H3O plus Cu2 CO3 goes to Cu2 plus HCO3 minus. Put my states of matter on there. I've been a little bit lazy today with my states of matter. But now that we actually have a solid material to worry about, I want to make sure I'm careful with that. And our K for this reaction, or your K total, K overall, whatever you want to call it, it's just going to end up being KSP times Ka. Whoa, times 1 over Ka. Right, the equilibrium, the HCl by itself, that just completely disassociates. So that HCl disassociating, we don't have to worry about that equilibrium, it completely happens. The equilibriums we have to worry about is how well is this carbonate going to take up protons, which is going to look at the 1 over Ka, and then how well is this copper carbonate going to disassociate in water, which is the KSP. So then I just take the KSP and the 1 over Ka values. So my 1 over Ka value is equal to 1 over 4.7 times 10 to the minus 11. And my KSP value is 3 times 10 to the minus 12. So I divide those over, and my K reaction ends up being kind of small. This is funny. I'm going to ask you a conceptual question after this. 3 times 10 to the minus 12 divided by 4.7 times 10 to the, times 10 to the minus 11. We get a K reaction, a K overall of 0.0638. Yeah?
For the KSP, on the sheet that shows up is just like copper carbonate. Is that just like how it wouldn't?
Yeah, so
the two?
the 2, oh sorry, we don't put the 2 here. Right, we know it's 2 because we know carbonate's a minus 2. If we write out the name, it would be copper 2 carbonate, and when we say it out loud, we'd say copper 2 carbonate. When we write it in a chemical reaction, we know it must be 2 because it's carbonate. I don't know what I was thinking doing that, sorry. Right, the fact that it's plus 2 is kind of implied in the problem. So, does this reaction make a lot of products? Is the Ka value bigger or smaller than 1?
Bigger.
0.0638?
Oh, no, it's not. It's smaller.
Smaller than 1. So that would suggest that we don't make a lot of products. So in nature, Why does this reaction go until all of the copper carbonate dissolves, like it goes to 100%? It turns out, this is an interesting thing. We see this all the time. It turns out soda goes flat, but not if you leave it sealed. Now, why does that matter? It turns out that this will go through a second step. And this question isn't asking about this, so this is bonus thinking stuff. Really interesting to me. So this reaction will go further. HCO3 minus with even a little bit of H3O plus around will form a little bit of H2CO3. Carbonic acid is one of those funny unstable acids though, and it dissociates to CO2 gas and H2O. So if you don't trap your products, the CO2 just escapes to the atmosphere and you never establish equilibrium. This second reaction happens even less. But every time you form a little bit of CO2, it escapes and you never reach equilibrium because your CO2 is always escaping. So if you don't do something to trap the CO2 so you can reach equilibrium, this reaction just runs off forever. Okay, other thing. You did the buffers lab. Yeah? What did you notice about the pH of deionized water?
It's not 7.
What was it?
Yeah, I don't know, but it messed up my problem. Well, it was like, I think it was low for me. I had a low pH. It was like
slightly
5.
higher than 7? Or...
Slightly higher is weird. Should be slightly lower. Should be like 5.
Oh, well.
No, no, that's not a problem with you. We've had one of the taps in the lab room has some contamination in it, and we've tried to figure it out, but its pH is coming out. We think the deionization system isn't working properly for some reason, and so it's turning the water slightly basic, which it's not supposed to do. But it doesn't seem to be messing up the rest of our experiments, so we haven't worried about it too much. The reason it's slightly acidic is because eventually the atmosphere has some amount of CO2 in it. So the water establishes some equilibrium with that CO2 in the atmosphere and forms some amount, there's an equilibrium here, and will form some amount of carbonic acid in your deionized water. That carbonic acid will then disassociate to put protons into solution. This is all the stuff they talk about with like global climate change and increasing the CO2 in the atmosphere. This CO2 dissolving into water is, I think, the biggest problem. Has anyone heard of acid rain or ocean acidification? Acid rain also happens with sulfur dioxide, but ocean acidification is happening because as we increase the CO2 concentration in the atmosphere, we're increasing the amount of CO2 that dissolves in water, which is increasing the amount of carbonic acid that's being formed. And we've got billions of years of, well, hundreds of millions of years of sea creatures that have developed systems of equilibrium to create calcium carbonate shells. If you increase the acidity of the ocean, their shells start to dissolve because the calcium carbonate goes through a similar reaction. So there's a lot of issues going on. Like every once in a while, there's these random like sea creature die-offs, and a lot of it has to do with algae blooms and other things like that. But ocean acidification, the coral reefs dying off is mostly because of ocean acidification. Slight pH changes can totally disrupt these systems that have, like, all of these sea life systems have established an equilibrium over millions of years of evolution to get there. And in the last 100 years, we've thrown that equilibrium way out of balance. And I'm totally fine if you want to say, no, it's just part of the natural cycle, but this is the first time we're here to observe it, and we've got some ability to control some of those equilibrium. So whether humans are causing it or not, we are. But whether we're causing it or not, we're in a position to do something about it.
Could you like genetically modify the calcium carbonate like creatures to like produce something that was a little more resilient to this like reaction?
That's a really interesting question. It's more than just the creatures, it's also the resources that the creatures have access to. And there's a lot of carbonate rocks in the world. Like, my first thought was, oh yeah, could you make calcium oxalate shells? And I think just the resources available, I don't know if it'd work as well.
Maybe you could
But-
give them resources, like you could make your own ecosystem and then.
Yeah, so now you're talking
Yeah.
about what is it, like terraforming,
Yeah.
right? Now
Yeah.
you're talking terraforming, which is if you've ever read the Red Mars series, it has some really cool science into the terraforming, into the idea of terraforming Mars.
That's sick.
It's a really long, like, it is. I'm gonna get sidetracked, but the Red Mars series has a lot of like really nerdy details about like if we wanted to terraform Mars with technology that existed in the 1990s, how would we do it? And it actually does a really good job of like going through like what details would need to be done, what resources exist, how could you turn like the surface of Mars like into bricks and build buildings out of like the materials that are on Mars already, with like bringing minimal devices with us from Earth. What could you do?
Yeah.
It's a cool book. Yeah, so that's competing equilibria, and we've talked about this idea of competing equilibria since the beginning of the quarter. We needed this. This goes back to our BCN lab with like the carbonates that dissolve and don't dissolve because of how strong the acid is. Right, this was actually on the first midterm where I was asking questions of like, hey, which things dissolve in strong acid, which things dissolve in weak acid, and it's like, well, in strong acids, anything that can behave as a weak base will dissolve to some extent. Like, my solubility has dramatically increased, still not bigger than 1, but my solubility has dramatically increased. And then we say, okay, what if we did a weak acid? If we had a weak acid, then we would need to worry about this first equilibrium that we didn't have to worry about this time. Number 23. Do me a favor, start on number 23. I see one of my other students in the hallway. I'm going to go see what questions they have. But go ahead and start on number 23. I'm going to pause the video for a moment. How do we do on number 23?
I think I'm good with.
Did you also
Did someone get 23?
Yeah, I did. Do you want to see?
What is number 23? Let's look at
It's
it.
a Lewis structure for NO3 minus.
Oh, it's just the Lewis structure for NO3 minus?
Yeah, but Lapal's kind of weird. Like if you don't add enough bonds, it automatically adds like a hydrogen. And then
Well, you need the negative
yeah.
charge, otherwise it'll add a hydrogen.
Right.
So if you don't explicitly, so if you just do NO, 2 double bonds?
1 double bond.
Oh,
Well, yeah, that's
okay.
right. Sorry.
Double?
It
Two?
looks like this.
Yeah. I don't feel like going through the whole process.
You're-
Oh, yeah, okay. So yeah, if you don't explicitly tell it that there's a negative charge on here, it'll automatically throw hydrogens on there.
right.
But when you throw the negative charge on there, it's like, oh, there can't be a thing there. And the nitrogen ends up with a plus because it's got the 4 bonds to it. So that's number 23. That's a throwback to Chem124, 127, and making sure we know how to draw Lewis structures. The systematic way, where I was being a little bit lazy a moment ago, I'll stop being lazy. We say nitrogen has 5 electrons. 3 oxygens would be 6 times 3, that would be 18 electrons. And then a -1 charge would be 1 more electron. So that's going to give me 18 plus 6. Is that 24? Yep, 24 electrons. I put my nitrogen in the middle. I put my oxygens around the outside. And then I try to get 24 electrons. If I just do 2 lone pairs on each oxygen, my nitrogen ends up without its full valence shell, right? I've only got 2, 4, 6 electrons around nitrogen. So I can take the lone pair off of one of those oxygens, turn it into a double bond, and now that has its lone pairs, that has its lone pairs, that has its lone pairs. But I have to recognize the fact that this nitrogen is in a plus state and these oxygens are in minus states for their formal charges. Formal charge, 1 through 5.
After a reminder.
So that is valence electrons minus non-bonding electrons minus 1/2 of the bonding electrons. And we're not going to use that a ton, but that's how we get this kind of like charged idea across the molecule. So we count how, and we have to do this on each atom. So if I take this nitrogen, let's do nitrogen for example. If I do the formal charge on nitrogen, I'm going to say how many valence electrons does nitrogen have? It's got the 2 s and the 3 p's. That's 5 valence electrons.
It's similar to
I look at it and I say it's got with 4 bonds to it. It's got no lone pairs. So that's 0 non-bonding electrons. And then I count up how many bonding electrons it has, which is 2, 4, 6, 8.
Oh, sorry, I just get you. It's really
So I end up with 5 minus 4. It gets me a +1 state on the nitrogen.
Right.
And then I have to repeat that for all of them.
I don't know why, but
And it's just the oxygens, having those minuses on the oxygen is necessary for the LabPal software to recognize that you know what's going on.
Yeah.
Yeah.
Okay.
Can you just count the bonds there?
You could. I like to keep everything in terms of the electrons.
I mean, but isn't that in terms of the
Same.
electrons?
Yeah.
It's just that you're only saying that it's sharing that many?
Yeah.
Okay.
Yeah.
Downtown, the Christmas one? I don't know, probably not.
On to 7.1.
Yes.
yes.
I had a question about 20 on 6.2.
Let's look at number 20 and then we'll go on to 7.1. What is number 20?
It's the relation between the original molecules and the other ones, like
Oh, I'm going to need more details.
geometric isomers.
Oh, that.
Oh, that question might be out of place.
Okay.
Someone asked about that in class, and I was like, why are you asking about that? So I rearranged the way I do these topics at the end of the quarter to give more time for hybrid orbital theory and molecular orbital theory, because it's more, like, I really like the transition metal stuff, but in terms of things you're going to use in the future, this stuff you're going to use more.
Okay.
So I switched things around. And I'll look at that problem. So I'll have to make a note to myself. It's 6.2, number 20.
Yeah.
Okay. So I'll make sure and look at that one and make sure it's fair. My gut reaction is to be like, oh, it's key terms. I'm sure you could figure it out, but I'll double check it still. Okay, 7.1, number 3, number 4. What's going on with 7.1, number 3?
It's what is that? Degeneracy.
Oh, that's a fancy word. What's it mean?
I don't know.
Degeneracy.
The number of orbitals characterized with the same energy.
Yeah. So remember today when I was like, this is the pattern, right? This is my sigma 2p.
Oh.
This is my pi 2p. This is my pi 2p star, and this is my sigma 2p star.
Right. Yeah.
Can you identify where there is degeneracy?
Oh.
Does this have any degeneracy? What's this one?
Yes.
Right, that's doubly degenerate. That's doubly degenerate. And that's it, right? Right. It's actually, you know, it's one of those things where that one is really like a key term thing.
Right. Okay.
It's like put a little arrow in here.
I think what threw me off was like with the same energy.
Right. So yes, they have the same energy. Remembering that the y-axis here is an energy axis. Whenever you have two marks like on the same line, they're degenerate energy.
Okay.
And that'll come up again when we go the little bit of time we're going to spend on what are those things called? The ligand field theory and transition metals will have multiple degenerate energy levels. We've actually had a lot of degenerate energy levels in the past, but we've just never called it that. when we look at the p orbitals and we've had them all in the same line, like my px, py, pz, that's triply degenerate. For my d orbitals, where I'm doing like my 5d orbitals all in the same line, that's a degeneracy of 5, right? I've got 5 orbitals all with the same energy. Those are referred to as degenerate energy levels. This is a key term.
What did you write under degeneracy?
Of 2. Sorry, my
Oh.
writing got a
I
little
thought it
bit
was
sloppy.
like point plus. I was like, what does that mean?
Degeneracy of, point plus 2. Everyone knows point plus. No, degeneracy of 2 because there's 2 energy levels with the same energy.
Got it.
Number 4, yeah? Or is that it for number 3? Cool. Number 4.
It's kind of hard to explain because there's like pictures associated with them.
Okay. So let's see here. Let's do 7.1. Number 4. May I take a look?
Yes.
Oh, yeah, okay. So each one is representing an orbital, and it wants you to get the orbital designation for each one. These are the pictures I was trying to draw today for the way that the p orbitals interact. These are a bit nicer than the ones I drew, but let's focus on C. Let's just do C together. Right, so C is this thing. I'm going to put the nuclei in there. I'm going to put the phase coloring in there as well. Right, that's how I draw it. They draw it a little bit different. But what does this look like? Weird bulbs, right? If you remember from what I was trying to draw in class today, this is like a p orbital here and a p orbital here constructively interacting. Do you see that? So that the entirety of 7.1 number 4 is just asking you to get comfortable with these like pictorial representations. You can look them up in the textbook, you can look at them in the lecture slides, or in your notes from class today. But we just have to come up with some label for this. This is going to be a 2p orbital with a 2p orbital, and it ends up with this geometry that's kind of flat in the plane. So if it's flat in a plane, we give it the Greek letter pi. And it's a 2p orbital, so we just call it pi 2p. That's the designation. And then the follow-up question to that is?
Number of electrons in molecular orbital C.
It's going to be 2 or 4. Now, I think it should just be 2. Now, why am I like, ooh, it's 2 or 4? Since it's only doing a picture of one of the molecular orbitals, each molecular orbital should only hold 2 electrons. But since this is the pi 2p, and I don't know if it's the px or the py, because there's degeneracy there, right? The pi 2p could be the pi 2px or the pi 2py. In my mind, it's drawing just a picture of one of them, and 2 electrons can fit there. I should go back and read the question more carefully to see if there's something in the text of the question that says as many orientations as it can represent or something like that. But my hunch is that it's only 2 since it's only one of the 2 drawings. Because I should have an identical but 90-degree rotated picture for pi 2py. So I think the answer is 2, but if it's kind of doing like either one that can be represented by this, it could be 4 because of the degeneracy. I think it should just be 2 though. 2 electrons per an orbital. And then it's similar logic for the other pictures, where it's just the way that those p orbitals are being put together. So kind of what we were doing through the middle of class today. Just kind of recognizing, so I can see the pi 2p, the pi 2p star, the sigma 2p, and the sigma 2p star. I'm not going to tell you which are which, but those are the 4 possibilities. Now, we know the ones that have stars should have should have minimal electron density between them. So which ones are going to be the stars? Right, the ones that are anti-bonding orbitals. You have to look at the pictures to make sense of it. A, B, C, D, which ones are anti-bonding? A and D, yeah. Which ones are bonding orbitals? Should be the other 2, B and C. How many electrons can fit in each orbital? 2. Unless they're taking the degeneracy into account, and we'll have to keep an eye on that. But I think it should just be 2 in each. Right, same thing we saw with our atomic orbitals. You can only fit 2 electrons per an orbital. Same thing's true for our molecular orbitals. Ta-da! We're done with all the questions. Oh wait, there's questions. Okay, question here. We'll go around the room. Yeah.
Sorry, can we do 8 for
7.1, number 8. Sure. Let's throw that on the list. We got 3 and 4 done. We'll throw 8 on the list.
I have a general question for my notes I want to ask you.
What's your general question?
It's I just want to go over question 5, but it's simply just answering the conceptual stuff. I want to make sure I understand it, so I want to.
Okay, is that 7.1, number 5?
Yeah, can I just ask?
Yeah. Well, let's look at it together. I think that's a good one to do. And then, what was your question?
It was how to do. It's like it's a 6.1 question. It was finding
The overall equilibrium constant one? Or am I thinking 6.2?
Wait, 6.2 number 5, not 7.1.
Oh, 6.2 number 5. Okay. What time is it?
2:26.
it was like question 9, 6.1.
6.1 number 9.
We did that one. like
Yeah.
an hour ago.
Oh really?
Yeah, so it'll be on the recording. I'm fine doing it again though, so don't worry about that.
I'll watch it on YouTube.
Well, I'll do these other ones and we'll come back to it as well if you want to hang out for it. Yeah.
I have a question regarding the
my
YouTube.
was plugged in.
I saw you posted office hours.
From Monday and something went wrong.
Okay, is that the 23-second video?
Yeah, I gotta figure out what went wrong. People during office hours today just told me that happened, so I haven't looked at it to see what went wrong. Most like the 2 possibilities are I messed up the recording, or I lost Wi-Fi while I was uploading. I'm hoping it's the second one because then the video will still exist. But I might not have my office hours from Monday recorded.
We're also gonna publish this too, right?
Yeah, of course. Unless I messed it up again. Yeah.
Can I also ask about the question 1 on the most recent quiz? It was like, which is a stronger acid, which is, I feel like that popped up and I still don't understand.
Okay, yeah. Relative acid strength?
Yeah.
Okay, let's toss that on the list. So I'm going to work through this list backwards since we're already doing 7.1 stuff. So let's do 7.1 number 8. What does 7.1 number 8 ask?
Oh, sorry.
Can I hand it to you?
Yeah, is it another long one?
Yeah, just like parts A through E.
Yeah, these conceptual questions where we're kind of like walking through things. After sketching the MO diagram for H2 in your notebook, do the following: write the valence electron configuration, determine the bond order. This is exactly, except for part C, this is exactly what we did in class today.
Okay.
Right? So the H2 MO diagram looks like this. Bop, 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 ding, bop, 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 ding. Actually, we did this on Wednesday. We got 2 electrons. We put our 2 electrons in. They're both in the lower. So the lowest energy MO is going to be this sigma 1s. The sigma 1s star is going to be the higher one. It says enter number of electrons in the lowest orbital. It's going to be 2 electrons in the lower orbital. Send knife to the next lowest. That's going to be the sigma 1s star. Number of electrons in that one is 0. Bond order is going to be 2 minus 0 times a half. It's going to be 1. Paramagnetic, diamagnetic key terms. This is going to be diamagnetic. And I probably will not count that. I think there's a graded question that has that. I won't count that against you. Correct effect. Will removing an electron increase or decrease the bond strength? It's key terms. And the problem with that problem, weird phrase. The problem with that problem is some instructors in 127 cover paramagnetic and diamagnetic, and some don't. And so that's where that problem, I used to just depend on classes in the past, but that has become an optional topic for people to cover instead of a mandatory topic for people to cover, and I need to adjust my questions for that. What's the highest, determine the highest occupied molecular orbital? Sigma 1s. This question is set up, the reason this question seems a bit weird, for H2, it's got way too much generality, but it's set up so I could do it for H2 or O2 or N2 or F2. Like it can kind of be, like it's set up to be generic for any of the diatomics. The one we haven't answered is, what would happen if we removed an electron? Would the bond order go up or down?
It would go down.
Yeah. Is that going to be a stronger bond or a weaker bond? Weaker bond. Removing an electron because, now, that's particular to this case because we happen to be removing an electron from a bonding orbital. Removing an electron from a bonding orbital makes weaker bonds, lower bond order. If we were looking at the oxygen example I did earlier today, right? If we remove an electron from O2, we're removing from an anti-bonding orbital. That will actually make the bond stronger and will send the bond order up. So you can't have a generic, removing electrons makes a bond weaker. It depends on where the electrons are in our molecular orbital. That's another new thing that we don't get until we do molecular orbital theory. And we'll keep working on that some on Monday when we start looking at the larger O2. Like on this, is the reason I'm okay with this assignment still being due today is because it's only about hydrogen and helium. So it's only those 1s cases. We'll spend more time looking at O2, N2, Cl2, those more complicated cases on Monday for 7.2. And actually, I think I'm going to push 7.1 back to Monday. Is that okay?
That's way better.
I meant to send that email out. I meant to send that email out after class, but I've been in meetings since class. I think that's probably why I'm so tired today. Yeah. It's been a long day. I still have class.
No.
4 to 6 p.m. on a Friday. So that was number 8. That was a lot of kind of talking through number 8. Did we already do 6.2 number 5? Are we revisiting that one? Or is that a different one?
Just like say
Oh, right, you wanted, yeah, so what is 6.2 number 5 doing? May I look at it real quick?
It has 3 general like conceptual questions
I think I can.
at the top right here, but I answered all of them. And I just
Oh,
wanted to get it
yeah.
right.
Do me a favor, read the question and then tell me what your answer is, and we'll see how you're doing.
So it's define the atomic orbital, hybrid orbital, sigma bond, and pi bond.
Okay.
So the atomic orbital, I put positions surrounding an atom's nucleus where electrons are most likely to be at any given moment.
Yeah.
Hybrid orbital created by mixing atomic orbitals on a central atom.
Yeah.
Sigma bond, I think I know those.
Cool.
Pi bond, I'm pretty good at that. But then it says, how does the number of atomic orbitals mixed relate to the number of hybrid orbitals formed? So then that's pretty much just like they're both equal to each other.
Yep.
Right? Okay, and
You
then
got here.
C, what role do the unhybridized orbitals play in a bonding model? What bond angles are associated with each? So then for that I put that unhybridized atomic orbitals form double bonds and pi bonds. Is that correct?
Yep.
That's all that it has to do with that question? Is that all that unhybridized orbitals do in a bonding?
Is that all?
Yeah, that's what I'm asking.
Is that all?
They can
That's
be all.
so much.
Really?
Yeah.
That's
So the unhybridized orbitals, they give rise to that double bond and triple bond possibility with those pi bonds that are out of the plane of the sigma bond. That are like planar bonds around the sigma bond. they also make it so you can have that conjugation, that delocalization of the pi electrons, which give rise to all those optical properties and give rise to those resonance structures. That does a lot in explaining these things that we have seen in the past, but haven't really been able to make sense of, right? Double bonds can't rotate. Why? Well, because we say so. Double bonds can't rotate because the unhybridized p orbitals form a planar geometry that resists the rotation.
So it forms double bonds, triple bonds, and pi bonds.
Well, double bonds, it forms the pi characteristic of double bonds and triple bonds. Remember, a double bond is a sigma characteristic and a pi. It's got that cylindrical symmetry and that planar symmetry. A double bond has both those parts. And the unhybridized p orbital is forming that planar, that pi characteristics of the double bond.
What do you mean by pi characteristic?
The pi characteristic. So when we form a bond, look at the pictures in the textbook. You're reading the textbook, right?
Yeah.
Of course. Okay. The pictures in the textbook are better than I can draw, and the pictures in my lecture slides are better than I can draw. But essentially what happens is we get this sigma direct overlap. I think I can do it in a 2D way. Right, so that is going to be like some SP-SP interaction, just for putting some label on it. But it's hybrid, it's direct hybrid orbital interaction. And then this, both above and below, I do it as a dashed line because it's not, it takes both of them. But that whole thing together, all of that bit in blue, is going to be the pi from the unhybridized PP interaction.
And that's why double bonds can't rotate, right? That's pretty much why.
Yeah.
Because of the side-to-side overlap, and the unhybridized p orbitals make it so it can't rotate because you need to break that overlap, right?
Yeah, right. So if I rotate one away from the other, I have to break that interaction, and that takes more energy than a typical rotation.
So if you break it, it's not a double bond anymore.
Yeah, you'd have to break the double bond in order to force it to rotate. And so that's a really important thing.
So double bonds are formed through that interaction?
Both the sigma interaction and this pi interaction together make a double bond.
Yeah.
We need both of those things to make a double bond. That's why I'm talking about the sigma characteristic and the pi characteristic. That cylindrically symmetric bit and that planar bit both are needed to make a double bond.
So then in single bonds can rotate because orbitals that form the sigma bonds are totally symmetric about internuclear axis.
Yeah.
Okay.
So if I rotate these two against each other, I'm not really changing any energy of that. Like they're still hitting in the same spot.
Yeah. Thank you.
You bet. So that was 6.2, number 5. Yeah, go ahead.
Something on that kind of topic.
Yeah, sure.
Can you explain the rotation around bonds for one of the molecules?
Which molecule?
It's 29. It's the one with the nitrogen and the, what do you call the long chain of single and double bonds?
Conjugated pi system?
Yeah.
Let's see. May I look at it? What do we got here? Okay. So that we've got this long. Okay, yeah. This one's an interesting one. Let's do this one. Right. So what we have to do to identify which bonds can rotate and which bonds cannot rotate is identify where this, and this is again where this hybridization comes in, and recognizing the conjugated pi system. Nitrogen. Oxygen. Double bond here, here, and here. Okay. So when we start asking, can these bonds rotate? Typically, we would look at this and be like, oh, a single bond can rotate. We have to be careful now. we have to recognize that there's resonance structures possible here, right? So because of the way that this is set up, I can have a resonance structure essentially where I've got my sp2, 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 right? I've got my sp unhybridized across this entire thing. And so I could equally have my electrons kind of shifted over here. And because they can have that shift over, I really have a delocalized system across this entire chunk. So everything in this conjugated system can't rotate. So I'm not going to be able to create any rotation through that entire conjugated system without some extra energy inputs to break that conjugated system of the electron kind of, the electrons being delocalized. And that's the phrase I tried to stress is we have these delocalized p electrons in the conjugated pi system was the phrase that I was using on Wednesday. It's these delocalized electrons, which makes it so there's only this orientation of all the unhybridized p orbitals pointing the same direction is the lowest energy situation for this. If I twist any of these away from each other, I'm going to interfere with that energy favorability. Okay. So while we previously would look at that single bond there and be like, it's a single bond, it can rotate, it actually can't. And the fact that that single bond can't rotate, again, is only really explained when we go to resonance structures because of our hybrid orbital theory. So in the past, if I was like, which bonds can rotate, like if we were in 127 and I said, which bonds can rotate, the double bonds can't. Actually, that single bond can't either because there's a conjugated pi system, there's resonance structures. So there's that extra detail that we didn't go into in the past that now we can start to think about because we have hybrid orbital theory.
So in ambient conditions, an sp2 and sp3 can't next to each other, connected to each other, cannot.
Well, so then this one over here, where I've got my hydrogens, this can rotate.
Yeah. So I'm saying if there's an sp3 linked to an sp2 by a bond,
yep,
that will always be able to rotate.
Generally, yes. I'm always reluctant to say always, but
even
generally,
if
yes.
On the other side, on the left side, let's say there's a double bond there.
Like this, that could still rotate.
Wait, is that a double bond?
No, that's a single bond. That single bond could rotate because there's no,
I mean,
right, it's sp3, sp3, so sp3 to sp3 could rotate.
Right.
This thing, sp3 to sp2, that could rotate.
I'm saying if you have a bond here, a single bond here, and then a double bond on one side and a double bond on the other side.
Well, so keep in mind, but you specifically said sp3 to sp2.
Yeah,
in order to have double bonds on both sides, that's sp2 to sp2. It's not sp3 to sp2, it's sp2 to sp2.
Right. Okay.
And that's why it can't rotate, because the unhybridized orbitals, again, are creating that energy preventing the rotation.
Okay.
So that's, again, the thing we're looking for is that sp2 chain giving rise to these resonance structures. The delocalization of the electrons creates that lack of rotation.
Thank you.
Okay. Back to 6.1 number 1. I think I'm going to stop the video, and we'll do 6.1 number 9 again. And what time is it? Oh, we got plenty of time for that. Okay.